Hello physics students, this is Mr. Steinerson, and in this video I'll be talking about the Doppler effect and beats when we talk about differences in frequency. First of all, the Doppler effect is probably not anything that's new to you. You've probably experienced this in real life when something coming at you, like maybe a siren from a police car or an ambulance, has a higher pitch when it's approaching you, and then when it zooms past, it has a lower pitch. That is, in a sense, the idea of the Doppler effect. And so you can see here in this diagram that there's a train emitting a sound from, and it's also moving at the same time. The observer here, every time the train is emitting a sound wave, it's spreading out in all directions, but the train is also advancing on the next wave that it's emitting. Therefore, the frequency will be higher on the front side of the train for an observer standing to the right. Notice how the wave is happening more often for that observer. Where on the other side of the train, where the observer is behind the train, the frequency is actually lower. The waves are spaced farther apart from each other. Therefore, the pitch that you hear is actually going to be lower. So basically, in a Doppler effect, if something's moving towards you, the pitch goes up. If something's moving away from you, the pitch goes down. So let's say we have a person that's also moving. How are we going to figure out what frequency they would be hearing as they are observing that sound? So, for example, if I have a sprinter, Usain Bolt, running away from a stationary trumpet or running towards a stationary trumpet, obviously when he's running away, the sound that he's hearing is going to be a lower pitch. But if he's moving towards it, it's actually going to increase the pitch and it'll go up as well. So when we take a look at finding out what that new frequency is, we have an equation. So this is something that we can kind of rely on when we're trying to figure out what the new frequency is, depending on if the observer or the source is moving. So f prime right here is the new frequency that's calculated. It takes the old frequency times this kind of factor, and this factors in if the observer is moving or stationary, and if they're moving towards or if they're moving away from the source. So what we're going to take a look at is the VA is the speed of sound in the air, and notice that is the same on the top and the bottom of this factor, plus or minus the VO. Now that is the speed of the observer. I'm going to talk about when we use positive and when we use negative here in the next slide, but pay attention. It could choose, you have to decide in your problem if it's going to be positive or negative. Same thing for the velocity of the source. That could be positive or negative depending on the situation. All right, so here's our equation. Take a few minutes and jot this down in your notes, and I'm going to go through an example using this equation. All right, so before we get to the example, I did want to reiterate the idea of what it means to have a positive or a negative VO in the equation or a VS in the equation. Now remember, this term that we're using here is going to be multiplied by the original frequency. So if it's greater than 1, if this whole term ends up being greater than 1, then the apparent frequency is going to be higher than the original one. So a person would hear a higher pitch. If it's lower than 1, if less than 1, then the person would hear a lower pitch. This makes sense. If you're coming at something, you're going to hear it higher, or if it's coming at you, it's going to have a higher pitch. And if it's moving away from you, it's going to have a lower pitch. So that's all that this term is doing in the equation, is looking at if the thing is approaching or if it's receding. So if it's approaching, VO will be positive, okay? So I would put positive in for that value, whatever it is, and VS would be negative. That creates a greater than 1 scenario here, so it's going to have a higher pitch. The opposite is true if it's moving away from you. The velocity of the observer would be negative in this case, and the velocity of the source would be positive. All right, so let's see how this looks like in this example. Take a quick look at the runner and make an educated guess. Do you think it's going to have a higher frequency or a lower frequency given the situation? So in the top situation, they're running away. Would that produce a higher frequency, or would running towards produce a higher frequency? Hopefully you said towards. And that's the logic that we're going to be using. In this example, I want to put a few numbers to what we've just been talking about logically. So in the first example, we have a stationary observer waiting for a train. And the train is moving towards the station at 31 meters per second, and it sounds a horn at 305 hertz. So this would be the frequency you would hear if you were on the train. What frequency would be detected by an observer who's standing next to the train and it's coming at them? Okay, so we need to look at our original frequency, which is 305 hertz. I'm going to add 0 for the velocity of the observer because it's stationary, and I'm going to have a negative for the velocity of the source because it is coming towards the station. Okay, so that's why it has a negative number there. All right, that's going to make this whole thing greater than 1. So that times 305 gives me 335 hertz. He's going to hear a higher frequency. Similarly, if a passenger is riding a train that's moving at a speed of 21 meters per second out of the station towards the other train, now the observer has a velocity as well. And it's going to be a positive velocity for the observer because they are moving towards each other. Keep the negative on the velocity of the source, and this still will have a value that is greater than 1, but it will have a different frequency that they hear. So that's the idea that I want you to do, is think about, are they moving towards or away, and adjust the velocity of either the observer or the source by adding positive or negative into the equation. The last thing we're going to talk about in this video is interference. And so with interference, we remember there are constructive or destructive interference scenarios, where in a constructive interference, waves combine together to make a greater wave, and if it's destructive, waves combine together to make a smaller wave. Well, that happens when we're looking at very similar frequencies. They will also combine together, and when that happens, when we have two frequencies that are very similar to each other and they combine together, we get a new wave that is formed, and it will oscillate loud and soft. We call that a beat. Now we can figure out the frequency of the beats, how often they're going to oscillate loud and soft, by looking at the difference between the two frequencies. So let me show you on the next page what I'm talking about here. So let's say we have two frequencies that are played together. This is often done when you're trying to tune an instrument and you're listening to the original frequency and your other note might be slightly off. You hear this pulsating sound, and that is the beat. So if one frequency is 400 hertz and the other is 400.5, the frequency of that oscillation and those beats would be a half a hertz. Similarly, if we have one at 400 and one at 401, then it would have a oscillating frequency of 1 hertz. Notice the farther they are from each other, the more frequent that beat sound is. So when you're tuning an instrument using this method, you want to try to get the beats to be very slow. So you hear the oscillation until it almost disappears as it slows down. So that's basically the idea of Doppler effect and beats. Please use this information as you're applying the calculations to our homework problems. Thanks.